Hello, this is the fourth video of Game Theory Series 2 for OCR Discrete Further Mathematics, and we consider the Nash equilibrium for zero-sum games. John Nash was a famous mathematician. You may have seen the film Beautiful Mind, or about him, whose work on game theory is influential in economics and other situations that involve decision-making. To understand what we call the Nash equilibrium, we have to think about what a player will do if he or she takes into account the strategy played by the other player, whilst they are making their own decisions on which strategy to play for themselves. So here's the matrix for a zero-sum game showing payoffs for player A. Now, it can be easier to follow what's happening while we discuss the Nash equilibrium if we write the matrix as an ordered pair of payoffs. So, player A may be called the row player and B the column player, and we can see that these ordered pairs are written in terms of the A payoff and the B payoff. We can see that because it's a zero-sum game, that these will be the negative of each other. However, this conversion to an ordered pair of payoffs is particularly useful when we are not dealing with a zero-sum game, which we'll look at later on. In previous videos, when we checked if games were stable or had a stable solution, we then looked at what the play-safe strategies would be for A and B. Here we're going to consider A's options for each of B's strategies in turn, and then do the same for B. And any choices that coincide will then form what we call the Nash equilibrium. In this payoff matrix here, we can see that if we knew that player A knows player B will play X, so looking down this column, what would A do? Well, if they chose P, they'd lose 4, whereas if they choose Q, they're only going to lose 1. So, choosing the least worst option, you would then have a QX choice. If player B was going to play Y, A would again consider and say, well, do I want to win 2 or win 1? And would choose to win 2. And therefore you would have that ordered pair as the choice. Now let's stop and think what B might do if they knew that player A would play P. Well, B has a choice between winning 4 or losing 2. So he or she is going to choose to win 4. And therefore you would have a PX situation. If B knows that A will play Q, then we would have a choice between 1 or -1, and B would choose to win 1 rather than lose 1, giving us QX. We can see that those are the same options, and you can see it from the underlining in circles, and that's the only situation where we have a circle and underlining for the same element of a payoff matrix. Thus we have identified that QX is the Nash equilibrium for this game. And this Nash equilibrium means that both players would choose not to change if they knew the other player's choice. Now, this doesn't mean it is necessarily the best possible outcome for them both. Simply that they wouldn't choose to change it even if they could guess their opponent's strategy. Now sometimes this is called the prisoner's dilemma, which we'll look at in the next video. And we can think of this as finding the column maximum values for A and the row maximum values for B. To determine whether there is a Nash equilibrium for this zero-sum game, first of all, let's set up the ordered pairs. I can do this because I know it's a zero-sum game, so I know that the B elements or payoffs will be the negative of the A elements. So then, let's have a think about what A would do if B was going to play X. Well, I think A would choose a strategy of Q and try and win 5. If B played Y, then A would go for R. And again, A would go for R if B was to play Z. So these are, if you like, A's choices, given that he or she knows what B is going to do. Thinking about it from B's point of view, if A was going to play P, then B would choose to play X, because they'd win 2. If A goes for Q, then B is going to choose either Y or Z, and we have 2 options here and we need to look at both of them, or list both of them. And finally, when A goes for strategy R, then B will go for Y as the least worst option. So are there any where we've got the same choices? And we can see that yes, RY does provide a Nash equilibrium. So they will both choose the option where A will win 2 and B will lose 2. But the Nash equilibrium can be found using the same method in zero-sum games, but also we'll look later on that we could use it for non-zero-sum games as well. Not all games have a Nash equilibrium, and some games have more than one Nash equilibrium. And the Nash equilibrium doesn't always give the best possible outcome for both players. In the next video, we will be investigating these ideas further and looking at the Nash equilibrium for other non-zero-sum games.